Okay, so to continue this first lecture with Science 30, I'm going to finish this calculation about coulombs, and then we're going to talk about gravitational fields. So I told you that this is the conversion. 1 coulomb equals 6.25 times 10 to the 18th electrons. So you might see a question like this. You have to be able to convert to electrons or from electrons to coulombs. So this says if 2.2 coulombs of charge is transferred to a lightning rod on top of Willis Tower in Chicago, used to be the largest building in the world, and grounded, how many electrons were transferred during a lightning storm? So remember this conversion factor, and then you convert units, right? So you cancel out coulombs, do your math, 2.25 times 6.25 times 10 to the 18th electrons. And then we end up with 1.406 times 10 to the 19th electrons transferred during this lightning storm in a lightning rod. Now, I also said when we were talking about pole flips, how do we know that poles flip? We know this because we can look at sort of mid-ocean ridges or volcanoes, and we can look at the geological record, and we can look at areas that have spewed out iron, and we can sort of, the further we look out from a mid-ocean ridge or a plate with plate tectonics, we can see the iron that's in the geological record. We can see layers of it where they're oriented, where the iron is oriented in a certain direction as a ferromagnet. And we know the poles flip because the orientation of that iron core in those geological layers, they flip every couple 100,000 years. So we can actually look at the geological record from volcanic eruptions and look at the old magma from past eruptions and look at where the actual ferromagnetic metal is in those rock layers, and then we can look at the electron orientation, and that's how we know that the poles flip. We also know that the Earth itself wobbles on its axis. So when the magnetic field increases and decreases strength, the Earth tilts a few decimals of degrees based on that. And that has caused past climate changes before. We call those Milankovitch cycles. It's called the wobble hypothesis, where the Earth might be tilted at 23.1 degrees rather than 23.5. That has to do with the magnetic fields of the Earth. Okay, so we have proof of the poles flipping in the geological record and understanding that Milankovitch cycles happen and things like that. Okay, so those are electric and magnetic fields. We'll talk about gravitational fields and electric and gravitational force. And then that should be it for the lesson today. Okay, so gravitational fields. So there's a question in this magnetic field lab that compares gravitational and magnetic fields. You know that there's field lines. You know that the strength of the fields increase or decrease based on the distance of the field lines from each other. There's a force of attraction in there as well, things like that. So gravitational fields. So here's the deal with gravity, right? Gravity is a really, really weak force, close up, but over large distances, gravity is the most important force in the universe. So gravity kind of governs everything and determines the structure of the overall universe. But on an immediate scale, it seems insignificant. So gravitational force is a universal force of attraction. It's a force that needs to be considered along with electricity and magnetism. A gravitational field is a property of the space around a source mass that enables the source mass to exert forces on other masses that enter the region. So gravity is dependent on mass. So mass is the amount of particles in matter that makes up an object. So every particle has a mass. So if you have more particles, then you have more gravity, right? So so mass is the amount of particles, right? So this determines orbits and structures of all objects in the universe. Okay, weight is the force of gravity of an outside body acting on you. So if I were to, for example, to hang out on Earth and then go and hang out on Mars, I would have the same mass because I'd have the same amount of particles. But because the gravitational field of the Earth is larger than the gravitational field of Mars, because Mars is a smaller planet, I would weigh more on Earth. So my weight would be more on Earth because the gravitational field is stronger and I would weigh less on Mars because the gravitational force is weaker because there's less particles that take up the matter on Mars. So you've got a couple equations here. This is in your textbook, and it's in your data booklet. So the gravitational field strength. So G is a function of the gravitational constant times the mass of an object times the radius of that object. Now gravity makes everything round in the universe. So we always use radius because particles are going to find the shape that makes them the closest to each other. All right, so the universal force of attraction makes things circular. So that's why things in the universe don't have sharp edges. All right. So the gravitational field strength is measured in newtons per kilogram. You need that gravitational constant, the mass, and the radius. So this stuff about gravitational fields and magnetic fields, page 328. You should do page 334. You should look at these questions, 12 through 15. Okay? So this is asking you to calculate the gravitational field strength of Earth at locations 2, 3, 4, and 5 from a satellite, right? So you have the distance from the Earth, right, which would be the radius, and you have and you have the mass. Okay, you have the mass of the Earth here, the mass of the Moon. Okay, so let's look at some of these questions. So calculate the gravitational field strength of Earth at locations 2, 3, 4, and 5. So let's look at 2. All right, shows a space vehicle on a mission to the moon. And you have the location 1 on Earth, 2, 3, 4, 5, 6, 7. So those are your locations where you do your calculations. So let's look at 2 right here. So the satellite or moon object in high Earth orbit is 2.0 times 10 to the 7th meters away from the center of the Earth. And so let's calculate the gravitational field strength of that. So for these questions, depending on if the object is closer to the moon or closer to the Earth, that will determine which object is more important in regards to gravity. So we know that G, that's my gravitational field strength, is a function of Gm over r squared. So to solve for this at location 2, on page 334, there is location 2, and it is 2.0 times 10 to the 7th meters away. If I look at my data booklet, big G is 6.67 times 10 to the negative 11. The mass of the Earth is 5.98 times 10 to the 24th kilograms. So when I put this all together, I have 6.67 times 10 to the negative 11 times the mass of the Earth, which is 5.98 times 10 to the 24 over the radius, and the radius is 2.0, yeah, 2.0 times 10 to the 7, and that is going to be squared. And then I solve for the gravitational field strength, and that will be in newtons per kilogram. Okay, so when I plug that into my calculator, all right, 6.67 e to the e negative 11. Multiply that by 5.98. 24. So I have 3.99 times 10 to the 14th up top, and then let's square that. 4 times 10 to the 14th. Okay, so 3.99 e to the e14 divided by 4. So my gravitational field strength is 0.9975. Newtons per kilogram. So relatively strong. Okay, and that's how, that's how I would solve for that. So you can do those other practice examples in here as well. Okay, so that's how we solve for gravitational field strength. Now you could, have to rearrange the equation, right? Be given the gravitational field strength and solve for radius and solve for mass, possibly. But that's just equation manipulation, so I'm not gonna get into a lot of detail about that. We should be familiar with how we do that. You could also have this, right? And you guys have seen this. Force of gravity equals mass times your gravitational field strength. So what's the force? Right, the force of gravity on Earth is 9.81 newtons per kilogram. And the acceleration due to gravity is 9.81 meters per second squared. So the force exerted on a test body by a gravitational field. So let's look. So that's what this addresses. On page 330, so I turn back a little bit. Okay. So here's an example problem. So Earth's radius has an average value of 6.37 times 10 to the 6 meters, while Earth's mass has a value of 5.98 times 10 to the 24th kilograms. Calculate the value of the gravitational field strength at Earth's surface, and predict the force of gravity Earth would exert on a person for B if they had a mass of 100 kilograms. All right, so here's how I would solve this, right? Solve for the gravitational field strength. Okay. And then my force of gravity in newtons, force of gravity equals mass times the gravitational field strength. So when I have 9.83, I multiply that by the mass of the person, and that gives me the force that Earth exerts on that individual. Okay, so Fg equals mg. That's on page 330. Okay, the other type of field strength that we're going to solve for is electric field strength. So electric field strength is the number of newtons per coulomb that a test body will experience at a given location from a source charge. The electric field strength is in newtons per coulomb. So we have newtons per kilogram with gravitational field strength. A coulomb, this is also in your data booklet, a coulomb constant is K. So the coulomb constant is K. 8.99 times 10 to the 9th newtons per meter squared, coulomb squared. And the C is the charge in coulombs, and the R is the distance from the source exerting the electric field, right? So electric field strengths, because they're more localized, are much, much stronger than gravitational field strengths, unless an object is really, really large, like a massive object, like a black hole. Okay, so this is why the Coulomb constant, so the Coulomb constant is much, much larger than the gravitational constant, right? And you can also solve for electric force, just like you can solve for gravitational force. So the force of electricity equals the energy times the charge. Okay? Right, and E would be the value that we would get of the electric field. So the energy of the electric field times the charge present. Okay. So in your textbook, page 336, there are example problems for how to solve electric field strength. Okay, so this is the example problem 1.6. You can walk through that. And you can look at the diagrams to see you have, right? So one thing that we need to deal with traveling in space is if we're going to set up a space station, we have to deal with ionizing radiation, right? So other planets don't have atmospheres to shield that out. So we would have to set up electric fields in order to absorb all that ionizing radiation, so it didn't, hit our bodies and then cause massive mutation, and we'd all have cancer. Okay, so electric field strength here. So you have practice problems on page 338. Number 16. Number 17 is an interesting one to look at. Okay, but this is an example problem. So let's say a balloon is given a charge of negative 4.5 nanocoulombs. So where you would get that N is data booklet times 10 to the 9. So N is, so that N is nano. So you'd automatically put a negative 10 to the 9 over top of that. So the question has to determine the electric field strength 30 centimeters from the center of the balloon. There's my charge. My distance has to be in meters. And I can solve for electric field strength. Right? So there's my charge, there's my distance. It's the same thing, right? R squared. And I would get an electric field strength of 4.5 times 10 to the second newtons per coulomb. So that would be my E value. So the electric field strength is an absolute value. All right, meaning that it's always going to be positive. And then, so for that answer, it's 4.5 times 10 to the second newtons per coulomb. All right, let's say the question then asks, solve for electric force. So force of electron is a function of the electric field strength times the magnitude of the test charge, okay? Okay. And the and the magnitude of the test charge is, right, was right, Q, and that was 4.5 times 10 to the negative 9 coulombs, right? We have that at nanocoulombs, and the electric field strength is 4.5 times 10 to the second. And that's Newton per coulombs, and that's times coulombs. So I can cancel that out, and I can get an answer in newtons. Okay? So when we solve for that, this is 4.5. Oops. And multiply that by and I get 2.025 times 10 to the 6 newtons. 2.025 2.025 times 10 to the 6 newtons would be my electric force. So we solve for the electric field strength. I already had the charge from the question. And then we multiplied, when we solved for the electric field strength, we multiplied it by the charge that was present. And then we're able to cancel out coulombs to get an answer in newtons. So that would be the force that would be exerting on that object, any object that would come into contact with that balloon. Okay? So this is Willis Tower in Chicago, so I was talking about lightning rods on that, right? So charges need to be grounded, right? So that's why large buildings have lightning rods. I'm going to see if I can give you one more question here. Just have to find it. Okay. So I'm going to give you two more questions and then I'm going to call it a day. In your textbook, if you want more practice questions for this kind of stuff, okay, page 346 has questions about gravitational field strength. Okay. Right, I already gave you some examples of electric field strength on page 338. But this unit okay, so the unit review, starts on page 405. Okay, page 406 has some more of these questions. Some voltage questions. Right, energy, charge, and voltage. Question 14 looks at gravitational force and electric force. Questions 15, yeah, so this is one big large question, 15A through G. Again, it's on page 406. That's all electric field strength. Same with question 16. So that's page 406, 407. But I'm going to give you two examples here. So, let's put this up. So the question says, I'm going to do electric field strength question. So the question asks, I'm going to put this up. Okay, so the question here for electric field strength asks, what is the electric field strength 7.5 times 10 to the negative 1 meters from an 8 microcoulomb charged object? Now, micro is mu, so you're going to see it like that. In your data booklet, there is micro right there. Micro is times 10 to the negative 6th. Okay, so electric field strength, right, is E equals K Q over R squared. All right, and what do I have for values? My K value is, for my data booklet, 8.99 times 10 to the 9. That's my K. My charge, Q, is 8.0 times 10 to the negative 6th coulombs, because it's microcoulombs. And my distance is 7.5 times 10 to the negative 1. And that's over R squared. So I can solve for electric field strength with that equation. So I'm going to expand this out. So when I do the multiplication, my numerator is 71,920. So I'm not going to do all the math on the calculator here. You guys can do this yourself. And I've got, when I square 7.5 times 10 to the negative 1, I get 71,920 over 0.5625. And my answer, when I divide that, will be 1.28 times 10 to the 5th newtons per coulomb. Okay, so that's how I would solve an electric field strength question. I'm going to give you a gravitational field strength question as well. And then I'm going to end my lesson for the day here. Okay? So, let's put this one on the board too. Okay, so the question says, calculate the gravitational field strength on the surface of Mars. Okay, calculate the gravitational field strength on the surface of Mars. Mars has a radius of 3.43 times 10 to the 6 meters. Okay, so Mars has a radius of 3.43 times 10 to the 6 meters and a mass of 6.37 times 10 to the 23rd kilograms. Okay, calculate the gravitational field strength on the surface of Mars. Mars has a radius of 3.43 times 10 to the 6 meters and a mass of 6.37 times 10 to the 23rd kilograms. Okay, so again, very, very similar to electric field strength, but the gravitational force uses this equation. So your gravitational field constant, right, is 6.67 times 10 to the negative 11. That's from your data booklet. We're going to multiply that by 6.37 times 10 to the 23rd. And that's going to be divided by the radius from the center of Mars. And that's over r squared. So it's the radius squared. Okay. When we solve for the numerator, when we multiply gravitational field strength times the mass of Mars, we will get 4.15 times 10 to the 13th. Okay? And then when we square the radius, we end up with 1.17 times 10 to the 13th. Okay, so when we solve for the gravitational field strength of Mars, okay, that's what you're going to end up using in a division question. So just as a reminder, if I plug this into a calculator, I like to, you can say hi to Jess.
Hi.
I like to break it up into steps. So here's, I'm going to write it like this, 4.15 e to the e 13, okay, and I'm going to divide that bracket by 1.17, 13. And I get an answer of 3.54. Yeah, 3.5